Welcome back. This is an introduction to trig functions and identities. In this section, we'll look at definitions of the trigonometric functions, Pythagorean identities, and area of triangles. Let's start with the definition of the trigonometric functions. In the previous outlines, we defined the trigonometric ratios for acute angles. Here, we extend the trigonometric ratios to all angles by defining the trigonometric functions of an angle. And this is just a lot of words, but notice that previously we were using the first quadrant, and now we are looking at angles that extend past the first quadrant. So now we have obtuse angles included as well. Let theta be an angle in standard position, and let P of xy, so the point xy, be a point on the terminal side. I'm going to go ahead and make that terminal point be in blue. On the terminal side. So if I look at how far this angle has rotated through along the unit circle, so to speak, we'll call this the xy axis, then we're looking at the point that can be found at the end of x and y. So we go to the left x and up y this time. We have a point P in the second quadrant, but this could also be extended into the third and the fourth quadrant as well. Let theta be this angle if r equals the square root of x squared plus y squared. This is just finding the hypotenuse. Then this is the distance from the origin to the point P, where we have a coordinate for x and a coordinate for y. And then it makes sense that this graph exists where x would be a negative number and y would be a positive number. Note that the inputs could be a positive real number or a negative real number based on how far we rotate through the xy axes. So if we were rotating so that our terminal side had a terminal point in the fourth quadrant, x would be positive and y would be negative. This is the same for output and the sign depending on the quadrant that the angle falls in. Since division by zero is an undefined operation, some of the trigonometric functions are not defined for certain real numbers. Because of this, we need to determine their domain. And below we have this list of trigonometric functions where sine of theta is y over r, cosine of theta equals x over r, tangent of theta equals y over x, and now notice that we have to define x to not be 0, because if we had 0 in the denominator, it would be undefined, and we saw that in previous videos. And then as we progress through the rest of these, y cannot equal 0 for the cosecant of theta because it's equal to r over y. Secant of theta has a restriction on x. The domain cannot have x equal 0 because secant of theta is r over x. And cotangent of theta is x over y, so y cannot be 0 because that would make all of these last four trigonometric functions undefined for 0. And you do need to memorize these as well. I think that goes without saying. But if you practice these a little bit, they're going to become second nature because we'll be using them all quarter. So as you can see, I've highlighted the trigonometric functions that will have a chance to have a 0 in the denominator. Notice that when you have a radius of 0, you're not going to have a triangle. It's just going to be a dot at the origin. So sine of theta and cosine of theta don't have any restrictions. And so you can see down here that sine and cosine do not have restrictions on their domain. It's all real numbers. But tangent and secant, we'll go ahead and underline these in bright magenta, or I think that's magenta. And so tangent and secant, those have all real numbers other than pi over 2 plus n pi. What that means is you start having undefined values for x when theta, the angle, equals pi over 2. And then the pi n, or the n pi, means that you will have the same thing happen for plus pi. That would give you the next value for which theta would be making the function 0. And then for plus 2 pi, plus 3 pi, etc. So when it says for any integer n, it could be plus or minus, because either way you wrap around the unit circle, you are going to continue to get undefined values for pi over 2 plus pi plus or minus 2 pi plus or minus 3 pi, etc. If you need to double check this on your own, go ahead and just draw the unit circle out and see what happens. And then for cotangent and cosecant, we'll go ahead and use brown for those. We've got cosecant here, and y cannot equal 0. And cotangent, y cannot equal 0. This will happen when theta equals pi or plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, and you get the idea. It continues on. Because this is an integer, so integers are whole numbers plus or minus. And as you wrap through the angles, you will see that at pi, y is equal to 0, plus or minus 2 pi, plus or minus 3 pi, etc., y equals 0. So go ahead and try that on your own with both of these scenarios to see where the domain can and cannot exist.